This is homework 3, part B of process dynamics and control. So what we have today is we're going to be deriving the closed loop transfer function for 3 identical gravity drain tanks. I've already got the diagram pre-made for the sake of time. And we're going to utilize this with a proportional only controller manipulating the flow into the first tank to control the liquid level of the third tank. And then we're going to finally use our final value theorem to show that the proportional control and the height of the third tank will always exhibit an offset relative to the set point that reduces with increasing controller gain, or a KC. So for making this a little easier, we're just going to rewrite this in a equation form. So what we will have is our Q in, which is our inlet, and what we're trying to find is H3. So what we're going to do is we're going to multiply essentially all of this within the boxes. So we're just going to make it cubed and then 1k squared. So we're going to have this multiplied throughout. So this is another way just to rewrite it. And then how we're going to rewrite this problem to suffice our problem statement. We also need a controller. So we have our Q in and we have our controller. This is going to go into our KC, and this is going to be our, this flow is going to be considered our error. It's going to go into GP, where GP actually just equals K, oh that's bad, K over tau S plus 1 cubed. It's pretty bad tau, but whatever. And then okay, actually one little thing, this is supposed to be our height set point. And then this is going to be our third, and we're going to have a recycle stream right here. I'm going to call GM, which this is going to be equal to just 1, and then this is going to go, oh that's really bad, goes straight into our controller. And then what we want to denote later, or now I should say, we want to know our forward and our open loop. So our forward values, essentially whatever is going in and then out, and then our open loop would be our current loop going this way. So to solve, what we're going to do is we're going to make our epsilon equal our set point minus our third height. Okay, so now I'm going to make our H3 defined. So what this will be is our KC times our GP, and then we're going to multiply that by our error, but we can just go ahead and make that our just P minus H3. Okay, and then if we go ahead and distribute that over, we're going to get KC times our GP, and then we're going to use this as 3SP since it's relative to those heights, minus KCGP times H3. Okay, so now what we want to do, we want to isolate our H3. However, we have 2 of them, so we're going to have to do a little bit of mathing. So if we move that over, we get this right here. And then if we substitute it out, we get KCGP equals KCGPH3SP. And then we can finally isolate our H3. So now we get GP, but I'll put H3SP on the outside for a specific reason, because this right here will be our transfer function. And how we can visualize this is by drawing. So if we have our box here, it's gonna outlet, it will be H3, then H3SP will be our inlet. This box will represent our transfer function. And that will cause us to rewrite this. So I use purple, yep. So we'll have to redefine our error a little bit. So which will be H3 times GM minus, I think this is supposed to be HSP actually. Actually, this is supposed to be flipped around. I actually had it right the first time. SP, which is going to represent what our closed loop would look like. So earlier it was an open loop where we went all around, but this time we're going to stop at GM. So now we can also state that our H3 is our GP times our GC, which represents our controller gain, times our error, which we can go ahead and plug in, which will be GC times our H3 GM minus HSP. And basically, if we go ahead and do the same math that we did above, to simplify this to get our isolated H3, what we end up with is GP times GC over 1 plus GP times GC times GM times our HSP. And this is our closed loop transfer function. Okay, so that concludes our part 1 of this problem. So now we're going to go ahead and set our final value theorem. So our FVT. And what we're basically saying is, in our limit where s approaches 0 in s times y, and this y is found through the Laplace transform, our limit of t approaching infinity is y, or of y, and that's equal to that. And then we're going to go ahead and restate our equation that we found. So C1 plus Kc times our GP times our set point. Okay, now what we're going to do is we can go ahead and also state that our set point will actually be A over S, where our A, or alpha, will be our input. So this is going to be important to figuring out that offset relative to the set point. And then if we recall from part A of our deviation variables, this will be prime. So then we'll see that our limit approaching s approaching to 0 of Rs times H will equal limit S approaching 0 of Kc times Gp times alpha over 1 plus Kc times Gp. What we can do is we can simplify this a little further by stating that Kc times K times alpha is over 1 plus Kc times K, and this puts our controller gain aspect back. So we can make our H equal to Kc times K times A over 1 plus Kc times K. And this is the equation that we would use using the FVT theorem, or the final value theorem. And basically what we're showing now is that the third tank will always exhibit an offset relative to the set point that reduces with increasing controller gain. So basically, as Kc will continue to increase, our value will continue to go towards 1, showing that there will always be that relative offset.